In this video, we'll learn about isrm. Isrm is a technique where you can prioritize your transitions into two sets, primaries and secondaries. And primaries are transitions that you monitor for the entire gradient. So for example, for 504 precursor and 515 and 793 transition, we are monitoring for the entire schedule window from 22 minutes to 25 minutes. And the moment these two primaries go above a certain threshold, the secondary scan is triggered. So as 22.95, we trigger a secondary scan, and we can see the scan right here. Let's go in here, and so at 22.95, this is how the secondary scan look. So we got all our 8 transitions for 504 precursor at 22.95, whereas we needed only 2 to be monitored for the entire gradient. So we can optimize the utilization of our dwell time and still get all of the 8 transition. And at 24.08, where again both the primaries went above the threshold, we again triggered our secondary scan and we got all our 8 transitions. And similarly at 25.04. So we can prioritize our transitions into primaries and secondaries, and then monitor only primaries and trigger secondaries as and when required. And how is isrm method built? I'll just give a very quick overview. In your, you need TSQ 2.2 software to generate an isrm file, and in that you would have a new method called isrm here. And once you go to isrm, you'd have these 2 additional categories called trigger and reaction category. And this is where you can specify what transition is going to primary and secondary. And your trigger is the threshold where the primaries are triggered to generate the secondaries. So how do we generate a primary SRM method? So to generate an SRM method file, we will add some proteins from our library, and we'll bring in a discoverer file. Let's go to the discoverer file, and we've added this discoverer file, apply library and close, and we'll select the interlace protein. That'll bring in all the identified peptides from there. Now, the idea for isrm is to prioritize transitions into primaries and secondaries. We will be using this pinpoint workbook to understand absolute quantification. So we have a bunch of peptides and proteins, and this is the light peptide, or the endogenous peptide, and this is the corresponding heavy labeled internal standard. We've added a whole lot of raw files which contain some of our curve points and unknowns, and we have grouped them here, as well as the groups show up in this column right here. This is the button that we'll use to understand absolute quantification. It's called absolute amount definition. Click that, and this window pops up. So first of all, let's go to this quantification strategy area. There are 3 options to do that: the standard normal curve, relative quan, and reverse curve. The standard normal curve is where you specify your the amount of the light spiked in every sample. So we have 10 femtomoles spiked here, and 50 femtomoles, and 100 femtomoles, and 250 femtomoles, and 500 femtomoles spiked in here. And all of my rest are unknown. Femtomoles in every file. And using that, every file will be a single point relative quan, and we'll compute the amount of the endogenous or the light peptide. So that's the second option. Any file having an unknown, nothing will happen with that file. The third option is reverse curve. In that case, we will specify the amount of the internal standard spike in, and that will be increasing. We'll use that curve to compute the amount of the analyte. This is especially helpful when we have endogenous present in the matrix that we're trying to quantify. And so our curve usually starts with a positive y-intercept. So you can try either this option or the standard normal curve. We will go with the standard normal curve for now, and we need to specify what units we are using and the weighting scheme. Weighting scheme 1 by x is usually the most common, but you can use 1 or 1 by x squared as well. So let's go with standard normal curve. We will not subtract for endogenous, and let's specify these amounts. So this 10, this 50, 100, 250, and 500. And then all of these are unknown. And as you can see, the moment I click unknown, the amounts disappear. because these amounts then have no, what you're saying is there's an unknown and there's no spike in. Okay, so apply and close. And we can again come back to this absolute amount definition after we look the data, and we can change something here and then look at the data again. Okay, so the data loads up, and you can see this first plot, which was used to be a histogram, now has become a curve. And clicking on any peptide, we can see this curve. So we clicked on this particular peptide, which has the light as well as the heavy labeled, and the light is normalized